Good evening. I am Jeong, Vice President of Quantum and Journal Club Major of QISCA. It is my pleasure to introduce today's Journal Club presenter, Woojin Jeong from Seoul National University. Woojin Jeong is a senior at chemistry education with a double major in physics and astronomy. He has interest in quantum technologies applicable in condensed matter physics, such as van der Waals quantum sensing and VQE for strongly correlated systems. Today, his presentation is titled Van der Waals Quantum Sensing, sharing insights from the papers, initialization, and readout for intrinsic spin defects in a van der Waals crystal at room temperature, quantum microscopy with van der Waals heterostructure, wide field imaging of van der Waals ferromagnet, iron, germanium, telluride by spin defects in hexagonal boron nitride, a single spin in hexagonal boron nitride for vectorial quantum magnetometry. Please welcome Woojin Jeong to the presentation.
Hello, I'm Woojin, a senior undergraduate student in Seoul National University. And today I will be presenting on van der Waals quantum sensing use spin defect in hexagonal boron nitride. This is the contents of our today's presentation. The van der Waals material are intrinsically two-dimensional materials, and they are easy to stack each other like something like Lego blocks. So many researchers have made various van der Waals heterostructures and find interesting physics such as unconventional superconductivity, tunable and programmable superconductivity, also such as like topological insulator and so on. But and direct imaging pattern of van der Waals material in spatial and momentum space, and the effect of straight magnetic field on van der Waals material are also the particular interest to many condensed matter physics researchers. To imagine this feature, many researchers have used tools like nanosquid and STM and MB Center in solid diamond. They've enabled high resolution local measurement, but share key limitations such like tightly controlled environments such like cryogenic temperature and ultra high vacuum. As you know, SQUID and STM need these conditions, and they typically assess only the top surface of the van der Waals material, and there is intrinsic limitation on physical distance between measurement device and material. With this point, I'd like to represent quantum sensing with spin defect in van der Waals material. The hexagonal boron nitride, which is also a van der Waals material, can contain negatively charged boron vacancy intrinsically through the exfoliation process. But we usually implant ions such as helium or nitrogen on an HBN with desired fluence to control the generation of defect. This defect has several characteristics. First, the peak of photoluminescence of this defect when we irradiate green laser on HBN is around 800 to 850 nanometers. And the defects from ensemble, not a single defect usually, so they can interact each other, and this spin-spin interaction can cause the decoherence of the spin on the spin of negatively charged boron vacancy. But some of you might be wondering, such the point, like, does this defect have a spin properties? Or if this is right, or if this defect contains spin properties, then how can we use this defect for quantum sensing? I'm going to tell you about this point. First, the answer of the first question, does this defect contain spin property, is yes, it contains spin property. The researcher finds that this spin defect has spin one property, not a spin half property like electron. So as you see in this energy diagram, uh, there are triplet ground state with the spin sublevel ms equal 0 and ms equal plus minus 1. When there is no external magnetic field, the ms equal plus minus 1 is degenerated. But if we apply the external magnetic field, there might be some energy splitting because of the Zeeman effect. So the degenerated ms plus minus 1 state is now splitted into two non-identical state. So we can manipulate these state with the laser and microwave easily. And this scheme is perfectly matched with the scheme of the spin qubit, such as a quantum dot or NV center in solid diamond. Some of you guys might familiar with this concept. And since this property, when we measure the optically detected magnetic resonance, magnetic resonance of this spin defect, we can see the quite uh, quite sharp 2D of the ODMR, and there are two resonance frequency. In this plot, they checked as nu1 and nu2, and usually the resonance frequency is located around a might be 3.4 gigahertz. Yeah, and so and this non-identical two resonance frequency means that there are some zero field splitting in this defect, even though there is no, even though the absence of the external field. To describe the details of the resonance, I will focus on the Hamiltonian of spin defect. This Hamiltonian describes the usual spin-spin interaction Hamiltonian. And from this Hamiltonian, we can easily calculate the two resonance frequency, nu1 and nu2. And the nu0 on the right side of the equation means the zero field parameter of the spin defect. And as you can see here, there is some magnetic field dependency of the resonance frequency of spin defect. So if we apply external field to the spin defect, the resonance frequency is also splitted. So as you can see here in the plot. So this splitting is the key concept of quantum sensing with the negatively charged boron vacancy in HBN, because the reason is on the next slide. I'm gonna tell you what is the detail of the scheme in the quantum sensing with boron vacancy in HBN. This is the figure from the main article of today's presentation. As you can see here, there are some sample you might be measured, and on the top of the sample, there is a HBM flake with spin defect, and you can apply laser, and you can apply microwave with the microwave antenna, as you can manipulate the sequence or the power or the frequency of the laser and microwave, we can manipulate the spin state of the spin defect in HBN. If we apply external field if we apply external field with quite high magnitude, which satisfy this condition, we can assume that the two resonance frequency nu1 and nu2 can be assumed this simple linear relation, not as this quite difficult relation. So if from this relation, we also can conduct the jet component, which is the out of plane component of the external field, out of plane component of stray fields of the sample, and from this, and also we can calculate the jet fields parameter with the resonance frequency. To be specific, I'm gonna tell you the experimental detail of this scheme. As you can see here, the dashed line, the dashed line represent the sample with the sample you want to measure the physics, and the HBN, which cover the sample. And when you measure the photoluminescence from this sample with the CMOS camera, which contain a lot of pixels in this area, there must be difference between there must be difference in the photoluminescence intensity in this region and this region, because in the previous slide, we can see that there is a metastable state, which represent non-radiating process of the spin relaxation, especially when the spin state is in the ground state with the spin sublevel ms equals 0. They might be excited to the excited state and relax to the ground state directly, not to cross the metastable state. However, in the spin state with the spin state in the ground state with the spin sublevel ±1, there are more population which relax to the process crossing the metastable state, which is the non-radiating state. So you can easily imagine that the ground state with the ms equals 0 might contain more intensity in photoluminescence than the ms equals ±1. So if we apply the resonance frequency in the microwave antenna and irradiate green laser to the sample, then the region in the sample surface should make less intensity for the photoluminescence than the region on the region of the region which not contain the sample. So there might be a difference of the resonance frequency, location of resonance frequency, and the next process is quite difficult. The next process is quite difficult, which is we should take all of the pixels of the camera and we should take all of the intensity data from the pixel, all of the pixels from the camera, and plot this ODMR graph and fitting with the double Lorentzian function for every pixels and find the difference between the resonance frequency of all pixels. Then we can find the out of plane field of the sample for all of the pixels. Then you can make the plot like this one, which contains the stray field of the van der Waals material we want to measure. So stray field, a stray magnetic field produced by the flake. On this article, they use chromium ditelluride and chromium ditelluride. So the stray magnetic field produced by a flake with in-plane magnetization is successfully measured by van der Waals quantum sensor with this scheme in the previous slide. And also, this quantum sensor can measure the temperature and the current imaging of van der Waals material. This figure shows the total scheme of the experiment to measure the temperature and make current imaging. As you can see here, there are two conducting metal gates on the edge of the graphite. And if we apply the bias voltage or bias current, we can see the Joule heating plot of around the graphene, because the spin defect of HBN also have temperature dependency, because the real general field parameter D is actually equal the D0, which is the initial general field parameter without the Joule heating, and minus alpha delta T, which is the alpha is the temperature constant and delta T is the temperature difference. So by this equation, we can calculate the Joule heating around the sample. And with this one, we can also conduct the current imaging of around the sample, because we can calculate the Weierstrass field of the sample with two-dimensional Fourier transform of two-dimensional real space current field. So with this calculation, we can easily imagine the current which is flowing through the sample underneath the HBN. So the ability of the HBN sensor looks like so cool, but the real experimental scheme is quite difficult, because we cannot apply the laser and microwave continuously to the HBN sample, because when we apply the laser or microwave continuously to the sample, then this continuous laser might overheat the sample over the Curie temperature of the sample. So if we want to see the ferromagnetism or the domain wall of the ferromagnetic sample, we cannot apply laser continuously, because this continuous laser might heat, and this heating can cause the case that the temperature of the sample might over the Curie temperature. So we should apply laser and microwave with pulse sequence, such as the same scheme of the Labi oscillation, which is used to obtain pi pulse calibration, or Han echo sequence, which is measure the extended coherence time T2 star. So with this with this pulse sequence of laser and microwave, we can successfully obtain the ferromagnetism property of the sample. So this article directly show the dependency of the sequence of experiment. When we apply the laser with pulse sequence, we can easily watch that the temperature difference of the sample is quite low, so we can successfully obtain the magnetic fields from the ferromagnetism of the sample easily. But if we match the probe point and the laser irradiation point, then there might be some thermal fluctuation of the sample. So we can check that the magnetic field from the ferromagnetism of sample is disappears somewhere. And finally, if we irradiate microwave and laser continuously, then the thermal fluctuation cause overheating of sample over the Curie temperature. So the magnetic field from the ferromagnetism is totally disappeared in this step. So from this point, we can imagine the magnetic phase transition of van der Waals ferromagnetism by manipulate the pulse sequence of measurement scheme. This article shows that by hitting the sorry, first I should tell that this article conduct the experiment under the cryogenic temperature because they use van der Waals material with van der Waals ferromagnetism material with quite low Curie temperature. So they should use cryogenic environment. As you can see here, through the increasing of the temperature, the magnetization of the sample is slowly disappeared or destroyed through the increasing of the temperature, and around the 169 Kelvin. Well, in my knowledge, the Curie temperature of the sample is 162 Kelvin or 160 Kelvin. Oh, okay. Anyway, then you can easily check that the pulse sequence can affect the measurement result of the quantum sensing. So we should use the pulse sequence, and from this figure numbered H, the calculated hole resistance is also shown that as temperature rising, the magnetization of the sample is decreased fastly around the Curie temperature of the sample. And the right side, I wrote the process of the calculation of magnetization in real field of the sample, but this calculation process is not difficult. It's not quite difficult, so you can easily check the process through the supplementary information of the article from this reference. So the total the presentation of this topic is over, and I'm gonna tell you the limitation and the future work of this topic. First, In the first slide, in the first part of the slide, I just tell you guys there are limitation of the physical distance of when we use nanosquid or STM to measure the van der Waals material. But actually, HBN quantum sensor also contain physical distance. It's physical distance limitation. In the Hillis work, which is the quantum microscopy, Hillis work, they use 40 to 70 nanometer thickness of the HBN with the thickness of 40 to 70 nanometer. And in the Huang's works, they use HBN with the thickness of 98 nanometer. So actually, there is no research done with the monolayer HBN, which is less than 1 nanometer. So it is hard to tell you guys that these quantum sensor can improve the limitation of physical distance of the tools such as SQUID or STM. And second, there is also a discoherence of spin defect because this defect contains spin properties. So the coherence time of the spin defect is usually known as less than 100 nanosecond at room temperature. In this point, I'm gonna in this point, there is something something wrong point that in the early part of the presentation, I just tell you guys that the limitation of the STM and nanosquid is that they should contain the harsh environment such as cryogenic temperature and ultra high vacuum. But from the current research, in my opinion, the HBM quantum sensor also need these cryogenic temperature or high vacuum environment to make longer coherence time of the spin defect. So I want to suggest the future work of this topic for these point. First, we should make research with sensing with few layer HBN. There are several works which conduct the experiment of sensing with few layer HBN, but it is not sufficient because they suggest the work with the HBN with thickness of few nanometer, such as like less than 10 nanometer, but not near the 1 or 2 nanometer. So we should make a quantum sensor with spin defect in monolayer graphene or bilayer graphene. And second, we should control single spin defect to reduce the decoherence of spin defect. The major reason of the decoherence in spin defect is spin-spin interaction with other spin defect or spin-spin interaction with spin death in the HBN. So we should make the work which can control the single spin defect to reduce the decoherence of spin defect. And finally, until now, there is no work which conducted the measurement of specific physics like superconductivity or ferromagnetism of van der Waals heterostructure, such as like magic angle bilayer graphene or other TMD system. So if we conduct the experiment with the quantum sensor on the van der Waals heterostructure, it might be interesting work for other people. This is the last slide of my presentation, and thank you for your listening. Is there any question?
Thank you for your great presentation. And I have a few questions. It looks Van der Waals material uses the Zeeman effect of the energy level, so that senses the magnetic field, right? And I think the nitrogen vacancy NV center has similar effect on the sensing. And so, what is the key difference between the uh, van der Waals quantum sensing and NV center sensing?
Yes, your question is exactly right. But there are key difference between the MV center and Van der Waals quantum sensing because as you can imagine easily, we cannot um, fabricate really really few layer diamond easily because diamond is quite hard to manipulate it. But Van der Waals material are easy to make few layer thickness because um, they are such a graphene-like material, so we can easily exfoliate it with Scotch tape. So uh, I think, in my opinion, the key difference is accessibility to low dimensionality. So we can uh, make lower dimension material with Van der Waals material easily, easier than diamond. So there is a uh, possibility to assess the shorter distance to the sample than the diamond because the bulk diamond contain intrinsic distance from the MB center and the sample from the sample. I think this is the key difference between them.
Thank you for your response.
Thank you.
혹시 그 한국어로 질문해도 되나요?
네, 괜찮습니다.
네, 때까지 그 세미나 설명해 주신 거로는 HBN이 한 층으로 이루어져 있다고 계속 나온 것 같은데,
아니요. 그 마지막에 그
네,
슬라이드에 봤던 것처럼 그 사실 그 모든 제가 그 이번 세미나에 들고 온 메인 논문들이 그 멀티레이어 그래핀으로 실험을 한 거예요. 그래서 그 마지막에 잠시만요. 어, 요 마지막 요 리미테이션 부분을 보면 이 HBN 실험을 한 이 힐리의 논문이랑 그 황의 논문을 봐도 얘네가 40에서 70 혹은 뭐 98, 그러니까 100나노 근처의 HBN을 쓴 거거든요. 그래서 실제로는 모노레이어 HBN을 쓴 실험은 아닙니다.
네, 그러면은
네.
자기장 지만 이펙트 때문에 피크가 두 개 말고 더 갈라질 수도 있는 거예요, 그러면 어떻게 보면. 그 축의
아,
방향이나 그런 것 따라 좀 달라질 것 같은데.
근데 이제 이 축의 방향이 달라질 수 있을 것 같은데, 근데 얘네가 제가 생각하기로는 이제 인트린시컬리 2D 매터리얼이잖아요. 그래서 그 단순히 우리가 이 Z축에 대한 그 자기장을 고려를 한다고 치면은 사실 뭔가 MV 센터랑은 다르게 MV 센터는 이게 오리엔테이션이 얘네 그 분자 구조가 이제 사면체가 막 이렇게 망상으로 이루어진 구조다 보니까 오리엔테이션이 그 익스터널 필드에 대해서 다 다르게 구현이 될 텐데 어 지금 이 2D 매테리얼 같은 경우에는 익스터널 필드가 하나로 이렇게 하나의 축에 대해서 고정이 되어 있다면은 그 축 방향으로 쉽게 폴라리제이션 할 수 있을 거거든요. 그래서 어 이게 스핀 앙상블이고 그리고 멀티레이어다고 하더라도 뭔가 아이디얼한 그런 두 개의 레조넌스 프리퀀시 이외에 다른 레조넌스 프리퀀시가 나오기는 쉽지 않을 거라고 저는 생각하고 있습니다.
그러면은 만약에
네,
자기장의 방향 같은 거를 더 알려고 하면은 어떻게
네.
해야 될지 센서를.
실제로 그 자기장의 방향을 계산한 논문들이 몇 가지가 있어요. 제가 그, 논문들이 있는데, 제가 그거를 자세히 안 읽어봤지만, 근데 걔는 제가 알기로는 그 익스터널 필드가 이렇게 방향이 바뀌면서 측정한 걸로 알고 있거든요. 그러니까 이게 저희가 실제로 그, 그 샘플의 마그네틱 필드를 측정을 하려고 해도 그 샘플 근처에다가 자석 같은 걸 둬가지고 익스터널 필드를 만들어 줘야지 얘가 이제 하이 필드 컨디션이 돼가지고 저희가 아까 근사했던 식처럼 그 뭐야 레조넌스 프리퀀시와 그 필드 간의 선형적인 관계가 유지가 되거든요. 그래서 실제로는 그 외부에 두고 있는 그 자석의 그 오리엔테이션을 바꿔가지고 어, 뭐 계산하는 것 같은데 제가 그 자세히는 그쪽은 안 봐가지고 지금 바로 답변 드리기는 어려울 것 같습니다.
네, 답변 감사드립니다.
아, 네, 감사합니다.
If there are no more questions, we will end today's presentation. Thank you, Woojin for today's presentation.